candidate designs, let's look at the desired traits in the transaction level assertions. So we would like these assertions to consist of communication primitives like function calls and events. We would like them to have parameters and return values included, and we would like these assertions to capture the fact that data propagation or data flow between the relevant blocks is the correct, we would like them to capture this particular relationship of data propagation between different blocks. So if you look at these two examples here, you see that the different attributes that we just spoke about are color coded. So TB write is a function call, DMA end transfer is an event, and SRC address shows data propagation, and such assertions cannot be generated by the decision tree based or the association mining based techniques. So in order to generate such assertions, we look at sequential pattern mining, which is a well known data mining method. Now sequential pattern mining searches for frequent subsequences as patterns in a sequence data set, and where a sequence means an ordering of events. So in this, so a sequence data set or a sequence database is this thing here where you can think of every one of these sequences as having a sequence ID or an SID, and here you see an item which is the most atomic or the most fundamental entity in determining these sequences, and multiple items form an element. Okay, so in this particular sequence database, you see that ABC is a subsequence that occurs in the sequence that's shown here. So given a support threshold of 2, which means that we want to record all patterns which appear with a frequency of at least 2 times, ABC is something that is recognized as a sequential pattern, and that's shown here in blue. It occurs twice, and hence this is considered a sequence. Okay, so now when we want to apply sequential pattern mining for transaction level models, or TLM as I've abbreviated it, how do we manage to map sequences and items and elements onto the transaction level primitives? Well, we use function calls or events as our most atomic unit or the item, and we use the tests from the simulation traces. Every single test in the or every single trace in the simulation corresponds to a sequence. Okay, so now if you look at our flow, then there is a pre-processing step that actually takes the function calls or events and converts them into items, and takes these tests and converts them into sequences in sort of a digestible format for the sequential pattern mining algorithm to determine subsequences of interest. Then after the sequential pattern mining tool actually comes up with these patterns, as we saw in the previous slide, are just patterns of sequences. So in order to convert them into a digestible format or an assertion format, we do some post processing and ultimately end up with this A implies B sort of format to form candidate assertions. Now beyond this, there is one more very interesting feature in the sequential pattern mining algorithm, and this is symbolization. So let's talk about symbolization and why we need it. So in a typical sequence database like the one shown here, let's look at what happens. So let's say there are 2 traces here, trace 1 and trace 2, and let A be the event that the variable V gets a value 12, let B be the event that Z gets a value 12, and C be the event that Y gets a value 14, and similarly A prime, B prime and C prime are events which assign to variables V, Z and Y respectively in trace 2. So if the sequential pattern mining engine looks at these traces and records them in the sequence database, then it will record A, B, C and A prime, B prime, C prime as separate events, thereby leading to the assertions A implies B, C and A prime implies B prime, C prime. But we know that these two assertions are not really different. They are not really separate assertions. Although they represent the concretization of certain variables, they fundamentally are talking about the same relationship between these variables. Okay, so these are not really different assertions. So the ideal version of these assertions is something more symbolic than explicit concrete events, and that would be something like, if V is delta, then Z is delta, is the same thing as V, and if V is delta, then Y is delta plus 2. Okay, so numerically whatever V is plus 2, right? So this kind of symbolization is what is desirable to make these assertions very valuable. Okay, instead of having hundreds of assertions which pretty much are saying the same thing. So to give you a more concrete example, if this is a source program in system C, then let's look at a concrete simulation. So a concrete simulation path actually assigns explicit values to every variable, and here you see that there's a concrete execution path, and where the DMA address, the source address is 2062. Okay, now in order to prevent explicit assertions for every concrete path taken, what we do is we try to get a symbolic execution of the same source program, and what the symbolic execution achieves is that this random number generator, or the random input, is symbolized to some delta. Okay, and once that is done, the same delta is propagated through symbolic propagation. We propagate delta throughout the execution, or we symbolically execute this code basically. And so when you come here, you see that even all variables, including the parameters and the function calls or the return values, are evaluated using symbolic input. So 2062 now becomes delta plus 1024. Okay, so 1024 is something that would be kept constant for in this example. Okay, so this is how symbolic execution and symbolization helps us generate much better assertions. Okay, so here we come to an experimental data. So now this shows a cycle accurate OR1200 RISC CPU model where we applied the coverage guided association mining, and we compared it to the original Goldmine decision tree based supervised learning algorithm, and we found that in every case the lighter bar graph, which the lighter bar, which is the coverage guided association mining, ends up producing fewer assertions than the decision tree, and it manages to have high coverage while producing fewer assertions. So this shows that the value per assertion of the coverage guided mining is much better than the decision tree based algorithm. In order to evaluate the transaction level model assertions, we used a typical AMBER based DMA controller, which I'm sure all of you are familiar with. It has a test bench, a DMA controller, an AMBER decoder, and 2 memories as slave devices. So we took a system C model of the same, and since as I mentioned, we do not have a validation metric for evaluating our assertions in terms of a formal engine or RTL validation. What we did was we created our own standards, which we think are important for assertions to subscribe to at the system level. The standard one is meaningfulness, which means that the parameters of function calls should be correlated and able to express data propagation type relationships. Standard 2 is scope, which means that the involved function calls and events should be at different interfaces on the design. And standard 3 is readability, which means that the number of function calls or events in the assertion should be no more than 3. So we just set 3 as a number or a constraint here. And this is sort of a representative sample of the kinds of assertions that we got, and you can see here that the standards that were met were either all 3 or at least 2 or 2 of the 3 at any given point. So let's examine one of these assertions, a couple of these assertions in detail. So one of these assertions that subscribes to all 3 standards says that if the DMA issues a burst read from a memory location with address A and reads data G, then a burst write will follow where G is written to another address location B. And since these are sequential pattern mining generated algorithm assertions, the assertions will always have the form, if something happens then something will follow, another event will follow. So this is just to give you an idea of what these assertions mean. And here we see why it subscribes to all three standards, because the length is 2. There are 2 events that are part of this assertion. Then the read as well as write interfaces of the DMA are involved, so the scope is beyond a single block, it's not intra-block, it's inter-block. And the common G, which is basically symbolic, shows that the written data is from the read call and the return value. So it shows that the same G is being propagated. This was extracted. Similarly, here is another assertion where we say that if the test bench calls the write function to configure the DMA and writes A to the source address register, then it's followed by a TLM API call where the first parameter or the source address is A. Okay, and now again this is only of this subscribes to all the standards because it's only of a length 2, and it includes both the write interface, which is in the test bench module, as well as the TLM call, which is from the DMA source code. And the address A is the symbolic address that's being propagated, so it subscribes to all our standards. Now in conclusion, we presented an automatic assertion generation methodology for system level models. So one of them works for coverage, so coverage guided association mining works for the cycle accurate level, sequential pattern mining for transaction level designs. And in order to make the sequential pattern mining algorithm generate more meaningful and succinct assertions, we use data symbolization by symbolically executing the system C code to improve the quality of assertions. That's all for now, and I'll take any questions on the conference call. Thank you.